Scientists study Earth's climate and the ways it changes in a variety of different ways, using satellites, instrumental, historical, and environmental records. One challenge of using satellite and instrumental data is that their lifespan have been rather short when compared to the Earth's life. The satellite record is only a little over 20 years old, and the instrumental record only extends back into the 19th century. Both of these records can be too short to study certain climate processes that occur over hundreds to thousands of years. Paleoclimatology, the scientific study of the climate conditions of the past geologic ages, so paleoclimatologists seek to explain climate variation for all parts of the Earth during any given geological period, beginning with the time of Earth's formation. Many related fields contribute to the field of paleoclimatology, but the basic research data are drawn mainly for geology and paleobotany. Speculative attempts at explanation have come largely from astronomy, atmospheric physics, meteorology, and geophysics. Two major factors in the study of both ancient and present-day climate conditions of the Earth are the challenge and the relationship between the Earth and the Sun, let's say the slight alteration in the configuration of the Earth's orbit, and the changes of the surface of the planet itself, such a phenomena as volcanic eruptions, mountain building events, the transformation of plant communities, and the dispersal of continents after the breakup of the supercontinent Pangaea. Some of those questions that were studied in the past have been largely explained. Paleoclimatologists found, for example, that warmth from the northern hemisphere landmass during at least 90% of the last 507 million years is mainly due to the drift of the continents across the latitudes. Until about 150 million years ago, both North America and Europe were much closer to the equator than they are today. Other questions, such as the reasons behind the regular advances and retreat of the ice sheet, as a glacial and interglacial episodes, are much more difficult to explain, and no complete satisfactory theory has been presented. To extend those records, paleoclimatologists look for clues in Earth's natural environmental records. Clues about the past climate are buried in sediments at the bottom of the oceans, locked away in coral reefs, frozen in glacial and ice caps, and preserved in the rings of trees. Each of these natural recorders provides scientists with information about temperature, precipitation, and more. Many of those have some type of layers, bands, or rings that represents a fixed amount of time, often a year or growing season. The layers vary in thickness, color, chemical composition, and more, which allows scientists to extrapolate information about the climate at the time each layer formed. Scientists can take the records left by many different types of natural records and combine them to get an overall picture of the global climate. Typically, records that have a large time span have less detail about short-term climate change, while shorter records are often more detailed. To combine them, scientists must use records of similar levels of temporal details or account them for disparity to accurately paint a picture in ancient climate. So the rocks is one of those. So today's landscapes gives clue to the climate of the past. Glaciers, for instance, left telltale signs in their activity. As the glaciers move slowly down river valley in the UK, for example, they often carved out a semicircular shape similar to the deep U-shaped valleys of Norwegian fjords. Glaciers also pick up pieces of rocks and gravel, and as they move forward, this debris scratches grooves called striations into the rocks on the valley floor. When the ice melts, the very large pieces of rock that has been carrying are dumped, often many miles from where they are picked. These abandoned boulders are called erratics. All of this kind of erosion and deposition clearly tell the temperature much colder than our current climate. The characteristics of different rocks depend on the environment in which the sediments were deposited. Some sands and gravels are dropped by glaciers as they melt and they become a distinctive rock called till. Where till is found, there must be glaciers, and therefore it must have been cold. Rocks that form in the hot desert environment are often colored red with iron deposits. Also, at high temperatures, seawater can evaporate quickly, leaving behind a layer of salt on the ground, which becomes preserved in the rocks and is another indicator of a hot climate. Fossils is another element that has been used as a clue. Some Pacific island nations are expected to be partially or completely submerged by the end of the century. Coral reefs live in tropical waters. They need a particular temperature, a specific depth of water, and the right amount of light. If the depth of the water changes just a fraction, they cannot survive. Different species of plants and animals need different conditions to survive. Some plants and animals can be very sensitive to climate and not adapt easily to change. Plants produce pollen and spores that are particularly useful in helping to determine climate. They are tiny, resistant outer case and are produced in millions. This means that they can be converted or covered in mud quickly, and they are more easily preserved as a fossil than large animals. Each plant has different shaped pollen or spores, so when the fossil is put under a microscope, it's possible to identify the type of plant it came from. Different plants are adapted to different climates. Therefore, looking at all the types of pollens present in the layer of rock can be a good indication of the climate and the time when they were alive. There is more. Also, the one type of oxygen and different types are called isotopes. So also can give some clues for us. Some of these isotopes are heavier than others, and this mass is determined by the number of neutrons the isotopes contain. Oxygen-16 contains 8 protons and 8 neutrons in each atomic nucleus. It's lighter than oxygen-18, 8 protons and 10 neutrons. In water, the relative amount of each type of oxygen varies with the temperature. Rain and ice contains water high in oxygen-16, so when there is a lot of ice in the ocean, water is left with a lot of oxygen-18. Shells and sediments carry the isotopic signature of the water in which they are formed. Therefore, by analyzing the ratio of oxygen-16 to oxygen-18 recorded in rocks, fossils, ice and sediments, we can find evidence that the climate at the time they were formed. On a particular note is the long story of drilling at the Russian Vostok station in Central East Antarctica. In Central Antarctica, the slow snow accumulation in polar desert conditions precludes counting, but the longest record are obtained here. The record for the longest span of time record is found in Vostok, high at the Antarctica ice sheet, possible extending back 400,000 years. Dating of such records, however, must be done indirectly by correlating them to other records such as the marine oxygen isotope stages, meltwater pulses seen in the sea level curves, or pollen. Vostok has not been drilled to bedrock. It is underlain by a subglacial lake some 500 meters deep that's being protected from surface contamination. Other Antarctic sites have also been drilled. In addition, it has long been recognized that the high-altitude glaciers near the equator or the temperate latitudes can supply a different view of a global climate. Mountain glaciers has been cored in the Andes, the Himalayas, and the Mount Kilimanjaro in Africa, very near the equator. Ancient and historic volcanic eruptions also can be detected in ice cores by measuring sulfate, SO4 or 2, concentrations in the ice. Sulfate being a major component of volcanic eruptions and form a sulfuric acid. Sulfuric acid is carried around the globe as an aerosol that strongly affects climate by reflecting sunlight back into space. Hydrochloric acid and hydrofluoric acid are also produced in volcanoes and are measured in the core as total acidity. These acids have a lesser effect on climate. These two cores have revealed more than 300 major eruptions over the past 9,000 years. The chemistry of the ash can often be tied directly to known volcanoes or ash layers in sediment. Many historic eruptions over the past 2,000 years are confidently tied to core data, and others can be approximately tied to other historical or geological data eruptions.